Alright, welcome. This is the Chapter 11 lecture video, and this time we are going to be conducting hypothesis testing for two different populations. Inferences on two population parameters. The first section has a ton of different learning objectives, and the first one, it's all about just distinguishing between independent and dependent sampling. All right, and so it's kind of means what we think it means. Independent is when individuals selected from one sample does not dictate which individuals is to be in the second sample. And the alternative is dependent, and we call those matched pairs when we have two different samples, but they are selected by matched pairs. So we need to be able to determine the difference between independent and dependent population samples. So we're going to look at an example here. And so this example, what we'll do is determine whether it is independent or dependent, and then we're going to identify the response variable and determine if the response variable is qualitative or quantitative. All right. So we have a college, and there are two different versions of a math class. One population is doing the lecture format, and in the other population, they're doing an online MyLab Math type of course. And we want to determine if the grades are better, if we have more passing grades in the lab-based format than in the lecture format. We want to know, are the students doing better grade-wise? So the sampling method would be considered independent because the individuals in the lecture format are not related to the individuals in the lab-based format. The response variable would be whether the students pass the class or not. So there's basically two outcomes, pass or don't pass, and we can calculate the proportion of students who passed by comparing the proportion to both of those samples. Here's another one. Are products purchased on Amazon less expensive than those purchased online at Walmart, right? And so what they decided to do was randomly buy 20 products from each different store, and then they decided to compare the prices of each. And so for B, the sampling method would be considered dependent because once the product is selected at Amazon, the same product is selected at online at the Walmart store. So this would be a matched pair design type of setup. Even though the prices might be a little different from product to product, it won't be different by much. And so that's why there would be a matched pair. The second objective is to test the hypothesis regarding two population proportions from independent samples, okay? And again, we're having two sample proportions, and suppose an SRS of size N1 is taken from population X1, where X1 of the individuals is the specified characteristic, and in the second population, the sample size will be N2, and it'd be independent, and X2 would be the individuals with the specified characteristic. And so if this is the case, we would then get the sampling distribution of p hat 1 minus p hat 2, where p hat is x1 over n1 and p2 is x2 over n2. That distribution will be approximately normal. The mean of the sampling distribution would be the same mean of the true population. And the deviation, though, would be the square root of all of this. Okay. And again, provided that n1 p hat 1 times 1 minus p hat 1 is greater than or equal to 10. And the same is true for the second population. And also, each sample size is no more than 5% of the population size. And the standardized version, we would, do this to get the standardized version there. And the best point estimate of the P would be called the pooled estimate of P. And so we would use that P hat there, and it'd be the sum of all the successes or the characteristics of each sample size divided by the sum of the two sample sizes. This is how we'd calculate the test statistic. Notice that that p hat is the pooled one, so the square root of p hat times 1 minus p hat. Hypothesis test regarding the difference between two population proportions. And so to test hypothesis regarding two population proportion P1 and P2, we can use the steps that follow, provided that the samples are independently obtained using an SRS or through a completely randomized experience with two levels of treatment. Also, we have this stipulation that N1 times P hat 1 times 1 minus P hat 1 is greater than or equal to 10, and the same is true for the second population. And then also, the sample size must be less than 5% of the population size that it came from. This requirement ensures the independence necessary for a binomial experiment. And so here are the different cases. A two-tailed test would be if we are determining that the alternative is between the two populations are not equal to each other. A left-tailed test would be to determine if the P1 is less than P2, and the right-tailed test between two populations would be to determine if the P1 is greater than P2. The second step would be to select a level of significance. Usually this is given, depending on the seriousness of making a type 1 error. 3. Compute the test statistic. And then once we actually have our test statistic, we will calculate the critical region, or if we want to just compare the critical value to the critical region, then we can now compare those two. Okay, so compare the critical value to the test statistic. If z naught is less than negative z sub alpha over 2, we would reject the null. If z naught is less than negative that, we'd reject the null as well. And then for the right-tailed test, if z naught is greater than z sub alpha, we would reject the null. So this is what would have to happen in order to reach a conclusive test. To reject the null and accept the alternative. And then finally, you would state the conclusion. Now, how would you handle this if you wanted to uh, end the test using the p-value? So we'd actually compute the p-value. The p-value is based on um, our test statistic, and we're simply comparing our p-value to the critical regions area. And if the p-value is less than alpha, then we'll reject the null, and then we'll state the conclusion. All right, so we're actually going to look at an example. So we have this clinical trial of adults, and a lot of things going on. Two groups. We have one group with the placebo, the other one with this. Is there evidence to conclude that the proportion of Nasonex users who experience headaches as a side effect is greater than the proportion in the control group? So let's carry this on. Let's just see kind of how this works. The samples are independent because the subjects were randomly assigned to the treatment. And here are the statistics here between the first sample and the second sample. So we calculate p hat 1 and p hat 2. And we also know that the requirements are satisfied. The samples are less than 5%. All three requirements are satisfied, so we can proceed through the steps. Step 1, we have to state our null and our alternative. So the null is that P1 is equal to P2, and the alternative is that P1 is greater than P2. We can state it this way as well. P1 minus P2 is equal to 0, and P1 minus P2 is greater than 0. All right. The level of significance is alpha. And now we're going to calculate the test statistic. First, we get the pull p hat, plug it all in, and we get 2.85. 2.85 is greater than the critical value of 1.645. So because the test statistic is greater than the critical value, we will reject the null. And then we can simply state that there's sufficient evidence to say that the alternative is greater. Now, if we wanted to calculate the p-value, again, we do the same thing, but once with our test statistic, we're going to calculate the area in that right tail. And the area in that right tail is actually 0.0022. We do normal CDF, lower bound, upper bound, 0.0022. That's less than 5%. Much, much less than 5%. So since the p-value is less than 5%, or 0.05, we must reject the null. There is sufficient evidence at the alpha 0.05 level to conclude that the proportion of individuals 12 years or older, taking that 200, I think it's like micrograms of that Nasonex, who experienced headaches is greater than the proportion who did not. All right. Now, how would we go about doing this on our calculator? Well, first, let's simply go back to the stats here. Let's pull up our calculator. And we're going to go to stat tests, and we're going to do a 2-prop z-test. This is number 6. x1, n1, x2, n2. That's what we're doing. Let's enter that in. x1, n1, x2, n2. And we believe that P1 is greater. And that's all you'd have to do. Again, you do have to make sure that before we conduct this, that all the requirements are satisfied. Hit calculate. And we have our test statistic is 2.83 or 2.84. Our p-value is 0.002, and that is much less than 5%, which is what we're going to compare it with. It's always best to do the test by the p-value. And then look at, they even calculated the pooled p-hat. Okay. So that was good to see that. Let's continue. And we're going to look at the third objective here. And this is to construct and interpret a confidence interval for the difference of two population proportions. So usually after you conduct the hypothesis test, if you follow it up with a confidence interval, depending on your results, it just makes a more stunning conclusion if they both coincide and support the hypothesis. So we are going to construct the hypothesis, our confidence interval here. Make sure all the requirements are satisfied. Here's the problem. All the requirements are satisfied. So here it is. The lower bound, we do p hat 1 minus p hat 2 minus this. And then p hat 1 minus p hat 2 plus this. And we actually get our confidence interval. And this could have been done using the TI-84. It's called the 2-prop Z INT. The INT stands for interval. 2-prop INT. Plug in the information, set your confidence level of 90%, and this is what you would get. The lower bound and the upper bound is consistent with what we got in our results. And then finally, determine the sample size necessary for estimating the difference between the two population proportions. Here is the formula. And there it is. So in this section, we're going to be looking at the inferences about two means from a population. Instead of two proportions, now we're going to focus in on the two means. And so in the first objective, we're going to look at testing a hypothesis from matched pairs of data. Again, the samples obtained using an SRS or some other matched pair design experiment. The data are dependent in this case, they're matched pairs. The differences are normally distributed with no outliers, or the sample size N is large. The sample values are independent, and the sample size, again, more than 5%, which ensures independence. Okay. So here we have the null and the alternative, and they're calling the mu sub d is the population mean difference between the matched pairs. All right, and the test statistic is given by this formula here. And again, we can do it two different ways. We can compare the critical value to the test statistic, or we can also do it using the p-value method. All right, same process. These procedures are considered robust, which means that minor departures from normality will not adversely affect the results. However, if the data has outliers, the procedure should not be used. And so here we have a matched pair design. The professor measured the time required to catch a fallen meter stick for 12 randomly selected students' dominant hand and non-dominant hand. Professor Neal wants to know if the reaction time in an individual's dominant hand is less than the reaction time in his or her non-dominant hand. A coin flip was used to determine whether the reaction time is measured using the dominant or non-dominant first, and then we're going to conduct the test at the 0.05 alpha level of significance. The data obtained were presented in the table 1. And here we have it. Each student, we have their dominant hand, non-dominant, so on and so forth. We compute the difference. And the sum of the differences here. And we calculate the mean and the deviation. We check for normality. The data appears to be checks out okay. And now we're going to conduct the hypothesis test. We're going to first state our hypothesis, that is the null and the alternative. We're going to calculate the test statistic next. And now we're going to compare our test statistic with that alpha level of 0.05, that significant level there. All right, our test statistic is much, much less, which means we do need to reject the null and accept the alternative. Our results are conclusive. We have enough data to conclude that the reaction time in the dominant hand is less than the reaction time in the non-dominant hand. The p-value is less than 1%, so it's clearly less than 0.05. So the reaction time, which is the lower number, we were looking for a smaller number. If you react faster, then the time that it takes you should be less. And now we're going to demonstrate how to construct and interpret confidence intervals. The upper bound and lower bound is given by this formula. There's our data. Keep in mind the calculator can do this. We would have to enter the data into two lists, one list for one category, second list for the next, and we go to t interval. And let's double check that calculator real fast and make sure that there might even be a 2 samples the interval test. Yeah, that's what I thought. You can enter it in, and if you have the data, you would just tell you what list it is and the little sigmas of each one, and the calculator will do the rest. Alright, so finally we're going to talk about 11.3, the inference about two means and the independent samples. There are two objectives here that, to test the hypothesis regarding the difference and construct and interpret confidence intervals. So sampling distribution of the difference of two means, the independent samples with population standard deviation unknown, is the Welch's t-test. And suppose that the simple SRS of size n1 is taken from a population with unknown mean, u1, and unknown deviation. In addition, an SRS of size n2 is taken from a population of unknown mean and unknown deviation. So in case we are going to use the student test t-distribution test, in order to conduct this test, these things must hold. There's our test statistic. Same steps as before. Same steps. It's the p-value approach. And now we have a problem. In the Spacelab Life Science 2 payload, 14 male rats were sent to space. Upon the return, the red blood cell mass of the rats was determined. A control group of 14 male rats was held under the same condition, except for spaceflight, as the space rats, and their red blood cell mass was also determined when the space rats returned. The project resulted in the data listed in Table 3 on the next slide. Does the evidence suggest that the flight animals have a different red blood cell mass from the control animals at the alpha of 0.05 level of significance? Okay, so we could probably look at it and see from eyeballing it and say, oh, there is a difference. That's just not enough. That's not going to hold up. We have to conduct a test to determine so. All right. The normality plots appear to be good. The straighter the line, the more normal the plot is. The more symmetrical the box plot is, the more normal it is. So we are going to move on, and our null and our alternative will be, we're going to conduct a two-tailed test here. We're going to assume that there is no difference, and the alternative is that there is a difference between them, whether positive or negative. We don't know. The level of significance is set at 0.05, and now it's time to calculate the test statistic. And we get a negative 1.43. That is not that negative, and this is a two-tailed test too. All right. Yeah. We did not collect enough evidence to reject the null. We can accept the null, it's just that we failed to reject the null. There may not be much difference. And so since the test statistic does not lie in that critical region, we do not reject the null. All right, and the same is true for the p-value method, which is the more preferred method. You compare the p-value with the alpha level. StatCrunch can do this for us as well. Here's a note about the degrees of freedom used to determine the critical value in the last example. Well, and this is again if you're not using technology. All right, now finally, objective 2. This is to construct and interpret a confidence interval. All right, and the lower bound and upper bound are given here, which our calculators can do this as well. And here is the scenario. A Gallup poll of 513 national adults aged 18 years or older who consider themselves to be Republican asked, of every tax dollar that goes to the federal government, how many cents of each dollar would you say are wasted? I guess it really depends on how do you define wasted. The mean amount of wasted was found to be 54 cents with a standard deviation of 2.9 cents. The same question was asked to 513 national adults aged 18 who consider themselves to be Democrats. The mean amount wasted that they thought was 41 cents with a standard deviation of 2.6 cents. Construct a 95% confidence interval for the mean difference in government waste. And then interpret this interval. We have to make sure that all the conditions are met. The samples are independent and obtained from an SRS. The sample size for both Republicans and Democrats are large, and the sample size is relatively small compared to the population. The requirements for constructing a confidence interval for mu minus mu of the Republicans minus mu of the Democrats using a student's t-distribution are satisfied. So now we can construct this confidence interval. Here are the sample statistics. You would enter this into the calculator at this point. We're getting that lower bound and the upper bound. So now we have an interval from 2.7 to 13.3. Using technology, we're getting that same thing. And we did use the pool 2 sample t-test when the 2 samples came from the population. All right. So now we've gone through the lecture videos, but I think it is important to just kind of preview some of the homework problems. We'll just kind of get a sense of what kind of problems are on there, how many, what kind of questions are they asking us here. Try to make the screen a little bigger. All right, yeah, these are pretty fair questions, pretty straightforward. In a survey, respondents were asked, would you be willing to pay higher taxes if the tax revenue went directly toward deficit reduction? What proportion of males who took the survey is willing to pay higher? What proportion of females who took the survey is willing to pay higher? The proportion of males and females who took the survey who are willing to pay higher. Okay, Yeah, and I guess what we're doing is the ratio of yes, because we want to know the ones who are willing to. It would be the proportion of the gender who said yes out of all of the genders of that gender, and vice versa, right? Now, if we were to try to open this in StatCrunch, it might be kind of hard to quantify how many people said yes and how many people didn't. I guess what we'd have to do is first sort the table. And probably from here, we would have to, we can assign a number. If it's yes, it would be a 1. If it's no, it could be a 0 or whatnot. Or maybe we can just sort this column as well. Okay, so it seems to me we would need to do some sorting, 2 levels of sorts. So first we would do by it would probably be better to open this in Excel actually. If we did Excel, we'd probably have a better chance at sorting this out real quick. We can do data sort this way. Gender, and then by yes to no or no to yes. No, that's not what we had in mind. Let's go back. Gender, and then all right. And let's flip that around one more time. We want our yeses first. This probably would make more sense. All right, so now we can count up all the females. There's a total of 120. Actually, we can subtract 1 because we're starting at 2. There's a hetero. So there's 120 females, and out of the 120 females, 48 of them said yes. So that's 48 out of 120. Okay, that's pretty much the way we'd have to do this. Kind of the manual way. I'm sure there's a lot of other ways, but we're not. I mean, we're just trying to be very practical. And then we would simply count up all the males from 122 to 201. The number who said yes, not that many. 123 to 141. So we got what, 201 minus 122. That's 79. And then how many yeses? That's from 122 to 140. It's like 18. So we're basically getting 18 divided by 79. These are somewhat similar, actually. I don't think they're that much different. I mean, let's convert that. 18 divided by 79 is 0.22%. And 48 divided by 120 is 0.4%. All right. So that's actually, there's more, but is that enough to say that women are more likely to pay more? They wanted us to round to 4 decimal places. I don't think I rounded to 4 decimal places, but I'll do point. The male we got to be 0.4, and female we got 0.2278. Hopefully this works. Actually, it's the other way around, huh? Male was 2278. The females was 0.4. It's even. No? I wonder if I'm off. How far off am I off? It's hard to say. It's not 48. Oh wait, is it? It is. It actually is 48. Yeah. 48 out of 120, and then the males Let's say from 122 to 201. $79. And of those, $19. So now I'm getting 19 out of 79 there. Okay. .2405. Yeah, we must have miscalculated. Looks like we miscalculated the mels there. Yeah, that's something you just have to be careful of. Yeah, seems like everything should be satisfied, although the number of mels wasn't all that great. We'd have to check that sample. I mean, we know what the real answer is, so you must well use the real answer, 0.2404, and then times 1 minus 0.204 times the sample size of 79. That should clear it. Alright, that was a good question anyway. Let's move on. It didn't seem like an easy way to do that problem, though. In the second section, we only have 10 questions, so it looks to me like it would float a little bit faster. Though some of the questions do seem a little challenging. Okay, so it's a matched pair design. You could probably do this entire experiment putting these into 2 lists, and then doing the. We'll probably make a video going over those as well. 11.3. Let's take a look. All right. All right, not too bad, not too bad. This question, they're asking a bit much. The least squares regressions line. We shouldn't have to do that here, not in this chapter. Some of these questions we might have to pull out. All right, so we are going to wrap it up here. As always, reach out if you want to discuss some of these questions a little further, and I'll make a video about it.